Hello everyone, I'm Joud. I lead a small security and privacy group at BBN, and this is joint work with SRI and UIUC. It's also part of the DARPA AA Bond program, probably with network design and deployment. So, what are hidden communication systems? A little bit of motivation. Imagine Alice wants to send a file to expel the file, and then there's this monitor that there's this monitor in the middle that's trying to detect, to find signatures of that activity. So what might Alice do? There's many ways Alice can do that. For example, Alice might encode the file bits into least significant bits of an image and use a ordinary network protocol like Mastodon to upload the image, and then use some other network protocol that Alice also uses on a regular basis, like DNS, to share this hash of the image with Bob, and then Bob can go and retrieve the image and retrieve the exfiltrated file. So here, what Alice has done is it's used an ordinary network protocol that it uses on a day-to-day basis to ensure that no signatures are visible by this monitor. So typically when we build these hidden communication systems, we have a fundamental trade-off between their performance and the undetectability. Okay, so the more information Alice sends, the more likely the higher risk of detection in general. And there's usually for users of these systems a requirement in terms of what this trade-off should be. Okay, so that because this is typically driven by the operational requirements. So today, the way we build these hidden communication systems is we design a system, we have a strong argument about its privacy properties, and then we go implement it, and we put a classifier in the middle, and we empirically test it and thoroughly as well, and we feel good about the privacy claims or the undetectability claims. And this approach has been artisan for the most part. So it is rigid, error-prone, and slow to evolve. What is missing is a formal and a general framework for these hidden communication systems and protocols, and for modeling the adversaries as well. So we want to be able to formally model all of it, the system, the adversaries, all the assumptions involved, and have a scalable way of analyzing these trade-offs quantitatively, okay? Also rigorous. And that's exactly also what we really want from these systems is that whatever guarantees we can achieve in these models, or we claim that these models achieve, they have to be aligned with the real world implementation, or otherwise we can't trust them. Okay? So that's exactly what we set out to do with this Maude-HCS toolchain. We can formally specify protocols, HCS, hiding within these protocols, background traffic, adversary capability, everything involved in the system. We can also express the properties, the quantitative properties like performance and undetectability formally and precisely. And then we can measure them and provide quantitative. We also formalize undetectability over trace distributions, which is an indistinguishability property. And we show how the framework is used to audit detectability claims, and we show strong predictive powers, as in the guarantees that we make in the models translate to the real test bed. Okay, so at a high level, I am not going to explain the formal models here in this 10-minute talk, but happy to discuss it later. I'll say at a high level, this is what the teaching looks like. So on the left, designers can specify formally all the elements here, so the underlying protocols, the transforms for embedding, the applications, and the adversary. And this is specified using rewriting logic uh, with its fine and probabilistic extensions, which is very natural for expressing uh, distributed uh, concurrent systems. Okay, and then these non-deterministic actor theories get translated, automatically transformed into probabilistic executable models using a pipeline that we also have in the T chain, such that these probabilistic models, the time probabilistic models, are aligned, semantically aligned with the non-deterministic models that you specify. And then given we specify the performance and detectability properties, and then we can make assessments over the system. Okay, to provide guarantees. So at a high level, um, this is our definition. This is how we, it has an animation got lost. This is how we define formalized undetectability. So there are two worlds, the ordinary world and the hidden communication system world. They differ in that in this world, we don't embed or hide information. An adversary observes traces from these worlds and is trying to distinguish between them. And this is formally what undetectability means, right? So it's parameterized by a divergence measure and some threshold over traces from these two worlds. Okay? And then given this formal definition, we can now audit an HCS system. And the way to do that is we have traces from these two worlds. We can compute using this Monte Carlo sampling, which is statistical model checking. We can compute true positive and false positive rates, convert those to a QL divergence measure. Right? And then if a system says has a claim about detectability, we can potentially falsify the claim based on that. Okay, so to show you some results, um, here is, for example, the sweeping, the operating point. So you see here on the left, as the client wait time decreases, it means we're sending more traffic. We see the certified KL lower bound increases, which is typically what we're going to see from these systems. Or we can also provide sweeping points for other parameters like the detector threshold for the adversary. And very importantly, what we've shown is that these systems align with the real world. So this is a test bed that is created by a highly qualified team, independent team that's evaluating the systems. So you see here on the x-axis different scenarios of different initial configurations, and we're measuring latency and output. In this case, there's many other measures that also align very well. Latency is the time it takes to processing the file, and we see the orange is the test bed empirical measurements of the real implementation, and the blue is what the model is saying is the latency. We see this aligned very well. So, so to conclude here, we presented we are building a formal modeling framework for reasoning for the HLF designers to be able to express and reason about the privacy performance trade-offs of their systems. We've developed a novel notion of distribution-based notion of undetectability over observable trace semantics. And we've evaluated the model and shown strong alignment. And we're currently working on significantly increasing scalability and adding an active adversary. And this is all open source, so I encourage everyone to use it. I'll say just two more things quickly here to wrap up. I don't have unfortunately, a official poster here, but I'll be standing next to one of the screens, so please come talk to me. And if you are a privacy researcher who is in the market for a job, please come talk to us also. We'd love to